Hello, ladies and gentlemen. Welcome to Lesson 1, Magnetism Intro. So here we're going to review magnetic stuff that you should know. I should ask, what do you know about magnetism? Well, for this, bales of Miltius the two of clubs on your deck of cards. So if you want to pull that out now, you will see that bales of Miltius, 624 BC to 546 BC, is credited with being the first person to write about static electricity using an example of a piece of amber rubbed with fur. So, static electricity. Now, getting back to magnetism. Should know north, south poles. Like poles repel. Unlike poles attract. Very much like charges. Like charges repel, unlike charges attract. Now, the ancient Greeks knew magnets produce a force on some metals. Now, a couple things to note. These are called ferromagnetic. Iron, cobalt, and nickel are the most common ones. Now also, this force is exerted at a distance. That's a field. So ferromagnetic materials, force exerted at a distance. You all should know that. Okay. Now once again, if I'm going too fast, pause, rewind. You know that. So going on. Faraday, or Michael Faraday, six of clubs. So pull out your cards again. Six of clubs. Michael Faraday, 1791, 1867. He used the concept of fields to explain electrostatics and is credited with the discovery of induction. Even though Henry Cavendish discovered it first, he got credit for it. Anyway, Faraday, you may know him more for chemistry redox. Anyway, Faraday. He developed the theory of magnetic fields. And electromagnetism, but that comes later. Now, with magnets, north, south, what do you know about magnets? All magnets produce a magnetic field, and the abbreviation for magnetic field is B. And notice it's a vector. Talk about absolute value later. The direction of the field is the way a test compass would point. So, here, the magnetic once again, think back to electric fields. You've got field lines, magnetic fields, we get field lines too. So, magnetic fields are represented by field lines. And I just made those the wrong color, so if I go back and change these to purple, there we go. There's my field lines. Now, note these are vectors. So, and like all field lines, the closer they are together, the stronger the field. Now, give you a moment to get that. When you're ready, go on to the next page, please. So very briefly, north, south. Goes from the north to the south. Now, if we do a horseshoe magnet, north, south, inside we get a fairly uniform field, but outside, and of course, like poles repel. You've all played with this. So it goes something like that. And note the field lines don't cross, ever. Now, what does this remind you of? Magnets, compasses? Well, I'm assuming you've played with compass before. You go out and you note the compass points to the North Pole. So if you're on Earth, here's the North Pole, the compass will point north, wherever you are. What's going on here? So field lines. Now, look at this and realize they're coming from down here, the South Pole, and what have you got? The North Geographic Pole is South Magnetic Pole. So, if we look inside the Earth, what we've got is not geographic north. What we've got is the South Pole here and the North Pole here. Now this has something to do with the fact that inside the Earth is a rotating molten iron core. Now, we don't completely understand it, but it acts as a giant magnet. And remember, iron is one of those ferromagnetic or magnet-inducing metals. So the Earth is actually a giant bar magnet. And if you want to get picky, the South Pole doesn't line up with the geographic North Pole. It's about 1,500 kilometers south on Baffin Island and moving towards Russia. So in a few thousand years, it'll be either in Russia or it'll flip. Again. By the way, that's the intro to magnetism. Now, that's the end of the first part. Go through this. If you want to go through it again, please make notes, whatever you feel most comfortable with. Once you've got this, go on to the second one, please. It's part 2.